And that is why you could think of hardness, meaning how hard is a specific input to solve, as a combination of two things. One is, I think, the size of the input, and we always measure this as a number n. But the other thing is the structure of the input. In a way, it's not larger instances are harder to solve, but in a way you could say harder instances are harder to solve. This, of course, might seem like a bit nitpicking around, so the question is this actually useful? And the answer is yes. For some problems, you can actually express the structure of the input, and I'm soon going to show you how to do that, as a number k. And while in classical NP completeness, so to say, you would measure hardness as some function of n, you can then measure hardness as a function of two parameters. One parameter is still the size of the input, and the other parameter is going to specify something about the structure of the input. Now, this might sound a bit abstract, so what could this parameter be? And I'm going to show you two possibilities for this parameter, and we're going to discuss them in detail. One is size of the solution, and the other one is something I would call distance from triviality. So for example, for the network from the last quiz, you could actually see that both parameters could tell us that finding a solution here is easy. Because first of all, the solution here, an optimum vertex cover, is very small. You only require one vertex. And also you could argue that this graph here is very trivial because all you need is a pre-processing rule to actually find the best possible solution. But again, we'll get into more detail. Let's start out with the size of the solution.